Today we start working with topic 8.4, which is the area between curves, and we're specifically going to work with our functions with respect to x today. All right? Consider two functions that are both continuous on an interval a to b. The region between the curves can be found by just subtracting the area of the upper region and the area of the lower region. All right? So when we have two curves, like we see in our pictures here, it really just boils down to subtraction. All right, on this first one, number 1 here, my upper curve is the upside down parabola. My lower curve is the right side up parabola. And so we just set up an integral right here where we're subtracting the upper minus the lower. Now, that's pretty straightforward, all right? It's pretty straightforward, but what we have to remember is which one is the upper and which one is the lower, all right? So let's get to some examples. That's the best way to tackle this. Let R be a region in the first quadrant enclosed by the graphs of 3x and x squared. All right? And if I want to find the area, I'm talking about this area in here. All right? That area between. And so I have to decide which one is on top, which one's on bottom, and in this case, the linear is on top. All right? So my integral is just going to be the integral from 0 to 3 of 3x minus x squared. This one's pretty easy. All right? Upper, again, upper function minus the lower function. That simple. All right? And we would find our antiderivative, which is, of course, 3x squared over 2 minus x cubed over 3, and we would evaluate it from 0 to 3, and so on. All right? To actually find the area between the curves. When you do all your work for that, you get that the answer is 9/2. All right? There's some other situations I want to get to, though, that have more involved than this one. Find the area of the region bounded by the graphs of y equals x squared plus 3. All right, that's our parabola that's been moved up 3 units. The line y equals x. Here's our line y equals x. And we have two vertical lines at 0 and 2. So the shading is correct on this problem. The shaded area is what we're looking at. So this is another one that's pretty easy. The upper function is the quadratic. So we're going to put it first, x squared plus 3, and we're going to subtract the lower function. All right? And we're doing all of this from 0 to 2. All right, and I'm just going to say finish normal, because this is pretty easy in terms of finding an antiderivative and plugging it in. All right? Like I said, there's other situations I'd rather get to. Let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs of y equals sine of x and y equals cosine of x as shown in the figure. Now, what I want you to notice on this one is there's no limits of integration. All right? There's no limits of integration, so we need to find the limits of integration on this one. That's the twist on this problem. We're not given what this x value is right here. We don't know what it is. We do know that we're starting at 0. So the bottom limit of integration is 0. But we don't know this one. So what we have to answer is when is sine of x equal to cosine of x? And you'll notice it does say in the first quadrant. So there's only one place, when we did all of our work with the bow tie and all that stuff, there's only one place where sine and cosine have the same value, and that's when we have a 45, 45, 90 triangle in the first quadrant. So back to our bow tie, that's 1, 1, square root of 2. All right. That happens, in both cases here. Both of these are the square root of 2 over 2. But what I need for this value right here is this value. But remember, we don't use degrees on the x-axis, we use radians. This value, 45 degrees, is pi fourths. All right. So that's kind of the kicker on this problem, is we had to find the limits of integration. And so I'm going to do the integral from 0 to pi fourths of the upper function cosine of x minus the lower function sine of x. All right. And of course, that turns into the antiderivative of cosine is sine. The antiderivative of negative sine is positive cosine. And we're evaluating that from 0 to pi fourths. All right. So again, if this is not a bad problem, you all should know what the sine of pi fourths is. We just said what it is. It's the sine of pi fourths is radical 2 over 2. All right, so this one should not be that hard to evaluate without a calculator. Keep going. Let S be the region of the first quadrant bounded by the graph of y equals the cube root of x, the horizontal line y equals 2, and the y-axis. All right, and so let's find the area of S. Well, again, they didn't technically give me the limits of integration. It looks like it's 8, but how can we be sure? Well, I just set the cube root of x equal to 2 and solve it. And that's pretty easy to solve. We cube both sides, and I do find out, we have confirmed that that value is 8. All right. So what is our integral? The top function in this case is a constant function. It's just the line y equals 2 minus the bottom function, which is the cube root of x, and our limits of integration are 0 to 8. Once again, the setup is what's key on these problems. Of course, we're assuming that you are a good calculus student and can find your antiderivatives okay. All right. This next problem is more of a calculator type problem. Let R be the region bounded by the graphs of sine of 2x and x cubed minus 2x as shown in the figure. Find the area of R. Okay. So once again, what is our upper function? Well, we know what sine of 2x looks like. That's this upper function. All right. So we're going to have the integral of the sine of 2x minus, notice what I'm doing, I'm putting the second function in parentheses so that I take care of my negative the right way. And I'm going from 0 to what? Well, they didn't give that to me. So using the graphing calculator, we can set these two functions equal to each other. I can graph the sine of 2x, and I can graph x cubed minus 2x on the TI-84 and look for the intersection point. All right? And that intersection point from the graphing calculator turns out to be 1.464. Again, that is a TI-84. I would put this into Y1, this into Y2, and find the intersection. So this little point right here is 1.464, and that's our other limit of integration. Then we could plug all of that into the graphing calculator, and we find out that the answer is 1.984. All right. Let's move on here. Let R and S be the regions in the first quadrant shown in the figure. The region R is bounded by the x-axis and the graphs of y equals 2 minus x cubed, which is labeled here, and tangent of x. The region S is bounded by the y-axis and the graphs of 2 minus x cubed and y equals tangent. Find the area of region R. All right. Well, this one is a little bit more persnickety. A little bit, we have to pay attention here. We have to split this one into two, because at this halfway point, the top function flips. All right? We need to do the integral of, notice, right here, this function is just the tangent of x. And there is no bottom function, it's just the x-axis. So all I have to do on this first part right here is just the integral of tangent. I don't have to subtract. All right? And that's from 0 to 0.902. Again, we would do that by setting these two equal to each other on the graphing calculator to find this 0.902. And then the other half is this area in here, and that part is again just a regular integral with no subtraction. It's just the integral of 2 minus x cubed, because it's just a function by itself, and we're going to go from 0.902, all right, to what? Well, it's going to be the 0 of 2 minus x cubed. And so that 0 is going to be the cube root of 2. So my top limit of integration here is the cube root of 2. Okay? Just trying to show you some setup on these problems. Now, if I was doing the area, find the area of S, this in here, now I do have a subtraction situation. This one, I would have the top function as 2 minus x cubed, subtracting the bottom function, tangent of x, and I'm just going from 0 to that 0.90, what did we say it was, 0.902. All right, so that region is a little bit different method, and we will stop there for today.